Picture this. You step out of a shimmering doorway in time, not onto the Mars of rovers and future astronauts, but onto the Mars of 1 billion years ago. You are not visiting the ancient, water-soaked world scientists love to imagine, the one with rivers and lakes and maybe even a northern ocean. That Mars vanished long before you arrived. Instead, you are standing on a planet that, in almost every way that matters, looks eerily like the Mars we see through our rover cameras today. The ground crunches with a fine, rust-colored dust. The sky above you is a pale butterscotch color, hazy with suspended particles. And the silence is absolute, broken only by the faint hiss of wind so thin it can barely be felt against your skin. This is the question we're chasing. What would it actually feel like? What would you actually see if you lived on Mars a billion years ago? The answer is stranger, and in some ways more haunting than most people expect, because a billion years ago, Mars had already become the frozen, wind-scoured world we know now. And it had been that way for a very long time. To understand why that's true and why it's actually one of the most fascinating chapters in the story of our neighboring planet, we need to go back much further than a billion years, back to the very beginning of Martian history, and then walk forward in time until we land exactly where our journey begins. Mars formed roughly 4.5 billion years ago, condensing out of the same swirling disk of gas and dust that gave birth to Earth, Venus, and the rest of the rocky inner solar system. In its earliest, most violent infancy, Mars was a molten world, its surface glowing, bombarded relentlessly by asteroids and the debris left over from planet formation. Slowly, over the next few hundred million years, it began to cool. Volcanoes erupted across its surface, releasing gases that built up into a thick, heat-trapping atmosphere. Some researchers now think that a huge ancient ocean may have covered close to a third of the planet's surface during this period, and recent modeling work suggests the young Mars may have been warmer and wetter than scientists once believed, with actual rainfall and snowfall carving valley networks that we can still trace in satellite images today. Geologists call this earliest chapter the Noachian period, stretching from around 4.1 to 3.7 billion years ago. And it is the era most people picture when they imagine ancient Mars, a place of rushing, rivers, standing lakes, and maybe, just maybe, the first fragile stirrings of life. But that Mars did not last. As the planet's interior gradually cooled, something happened that would define everything that came after. Mars lost its global magnetic field. On Earth, our magnetic field acts like an invisible force field generated by the churning molten iron in our planet's core, and it deflects the relentless stream of charged particles that our sun constantly hurls outward into space, a stream known as the solar wind. Mars, being smaller and cooling faster than Earth, saw its internal dynamo shut down. Without that protective magnetic shield, the solar wind was free to slowly strip away the Martian atmosphere, molecule by molecule, over millions and millions of years. It's a bit like leaving the cap off a bottle of soda. The pressure that once held everything in place slowly, inexorably, bleeds away. As the atmosphere thinned, Mars lost its ability to trap heat. Global temperatures plummeted. The rivers stopped flowing. The lakes dried into cracked, salty basins. The great transition from a warm, wet world to something more like the desert we know began roughly 3.7 billion years ago, in a period called the Hesperian, and by around 3 billion years ago, that transformation was essentially complete. This brings us into the era we actually care about, the one you're now standing in. Scientists call it the Amazonian period, and remarkably, it's the epoch we are still living in today. It began roughly 2.9 to 3 billion years ago, and it has continued, largely unbroken, for the entirety of Mars's more recent history, which means that when you step onto the surface a billion years ago, you are stepping into a Mars that would already have looked deeply, unsettlingly familiar to anyone who has seen a photograph beamed back by curiosity or perseverance. The wild, dynamic, river-carved Mars of the Noachian was already ancient history, over 2.5 billion years in the past, further removed from you than the earliest multicellular life is removed from modern Earth. You have arrived not at the beginning of a story, but somewhere deep in its long, quiet epilogue. So let's talk about what your daily existence would actually involve, because this is where the science gets both eerie and strangely beautiful. The most immediate thing you'd notice is the air, or rather, the almost total absence of it. The Martian atmosphere today is barely 1% as thick as Earth's, made up overwhelmingly of carbon dioxide, and there's compelling evidence that by a billion years ago, the atmosphere had already thinned to something very close to this modern state. Standing on the surface, you would feel a pressure so low that liquid water simply cannot exist there for any length of time. If you poured a cup of water onto the ground, it wouldn't puddle and slowly evaporate the way it would on Earth. It would boil almost instantly at room temperature, not because it's hot, but because the pressure pressing down on it is so feeble that the water molecules can escape into vapor almost as fast as you can pour them out. This single fact reshapes everything about what survival on this Mars would mean. Without a pressurized suit, your own blood and saliva would behave in eerily similar ways. This is not a world where you casually breathe the air. Without technology, this Mars kills you in minutes, not from cold or radiation first, but from the simple physics of exposing your body to a vacuum-adjacent environment. Then there's the cold. Average temperatures on this Mars hover around a bone-deep 60 degrees below 0 Celsius, though the range swings dramatically. On a summer afternoon near the equator, you might momentarily experience something close to a chilly spring day on Earth, perhaps 10 or 15 degrees above freezing at the surface. But the moment the sun dips, temperatures crash catastrophically because that thin atmosphere holds almost no heat. Nights would plunge to temperatures cold enough to freeze carbon dioxide directly out of the air as frost. Imagine a world where the very air can snow onto the ground as dry ice. Above you, the sky itself would look different from Earth's, in ways that are subtle but constant reminders of where you are. Because the Martian atmosphere is so thin and filled with fine dust particles, the sky often appears a hazy butterscotch or salmon color during the day, rather than blue. And in a strange inversion of what you'd expect, sunsets and sunrises on Mars can actually turn the sky near the sun bluish. Because the dust particles scatter blue light differently than Earth's thicker, nitrogen-rich atmosphere does, the sun itself would appear noticeably smaller and dimmer than it does from Earth, since Mars orbits roughly 1.5 times farther from the sun than we do, receiving less than half the sunlight intensity. A full Martian day, meanwhile, would feel oddly familiar, since Mars rotates on its axis roughly every 24 hours and 37 minutes, remarkably close to Earth's own rotation period. But a full Martian year would stretch on for nearly 687 Earth days, almost double our own, meaning the seasons themselves would drag on for what would feel, to a transplanted human, like an eternity. Now, you might assume that 1 billion years ago, geologically speaking, nothing at all was happening on Mars, that it was simply frozen in time, a dead world going through these motions. But that turns out to be only partly true, and this is where some of the most fascinating and recent research comes into play. While Mars during the Amazonian period was overwhelmingly quiet compared to its violent youth, it was not completely still. Scattered across the planet, particularly in the Tharsis region, colossal volcanoes continued to erupt sporadically throughout this long, quiet era, including Olympus Mons, the largest volcano in the entire solar system. To put its scale into perspective, Olympus Mons rises roughly 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest, and its base sprawls across an area comparable to the size of a small country. If you were standing on Mars 1 billion years ago and happened to be anywhere near this monster, you might have witnessed slow, oozing lava flows spreading across the landscape, releasing plumes of gas that, for a brief geological moment, could have locally warmed the surrounding air and even triggered temporary melting of subsurface ice. Recent geological studies examining regions like Hydrauot's Chaos have found tantalizing evidence that volcanic heat, welling up from below the crust, may have melted buried ice as recently as 1.1 billion years ago, sending brief pulses of liquid water flooding across the surface before it refroze or evaporated away. These would not have been rivers in the ancient Noachian sense, vast networks carving continent-spanning valleys, but rather short, localized, almost violent bursts, geological hiccups in an otherwise silent world. Ice itself tells an equally remarkable story about this era, one that has only been pieced together in real detail in the past couple of decades through high-resolution orbital imagery. Mars's axial tilt, unlike Earth's, is not stabilized by a large moon. Our own moon acts like a gyroscope, keeping Earth's tilt locked within a narrow, stable range over millions of years. Mars, however, has only 2 small, irregular moons, Phobos and Deimos, far too tiny to provide that stabilizing effect. As a result, over hundreds of thousands to millions of years, Mars's axial tilt has wobbled dramatically, at times swinging far more extreme than Earth's ever does. During periods of high tilt, the poles would have received intense sunlight, potentially destabilizing polar ice and driving it toward the equator and mid-latitudes, where it could have accumulated into vast ice sheets and glaciers, kilometers thick in places. Researchers studying the glacial deposits and landforms of this Amazonian period have found evidence that entire glaciers advanced and receded across Mars's mid-latitudes repeatedly over the last 1 billion years, a kind of Martian ice age cycle distinct from anything happening on Earth, driven not by orbital wobbles interacting with ocean currents, but by the chaotic tumbling of a planet with no moon large enough to keep it steady. Standing on Mars 1 billion years ago then, depending on precisely when and where you arrived within that vast stretch of time, You might have found yourself not in a bone-dry desert at all, but at the edge of a slowly creeping glacier, a river of ancient ice grinding its way across a landscape otherwise devoid of any visible water. This brings us to perhaps the most exciting piece of the puzzle, and one that has only come into sharp focus in the last year or two of active Mars exploration: the question of what chemical and possibly biological remnants might still exist from that vanished wet history, and whether any of that story continued into the era you're now walking through. In 2025, scientists analyzing data from Curiosity's long-running exploration of Gale Crater identified deposits of siderite, an iron carbonate mineral, in rock layers formed through reactions between water and rock less than 1 billion years ago. This was a profound discovery, because it suggested that a portion of Mars's ancient carbon dioxide atmosphere had been chemically locked away into rock through a genuine, if limited, carbon cycle, one that continued operating far later into Martian history than most scientists had previously assumed. It hints that even in this quiet, cold Amazonian world, water was still occasionally interacting with rock and air in ways that echoed, faintly, the planet's warmer past. Even more remarkably, throughout 2025 and into 2026, both the Curiosity and Perseverance rovers made a series of discoveries that have reignited excitement about the possibility that Mars once hosted the chemical ingredients necessary for life, and that some of those ingredients have survived, astonishingly preserved, for billions of years. Curiosity's onboard chemistry laboratory identified an unprecedented diversity of organic molecules within mudstone samples drilled from Gale Crater, including compounds called nitrogen heterocycles, ring-shaped molecules, considered possible chemical precursors to DNA and RNA, the very building blocks of biology as we understand it. Meanwhile, on the opposite side of the planet, Perseverance's instruments detected complex macromolecular carbon within a rock formation called Bright Angel, located along an ancient river channel that once fed into Jezero Crater's long-vanished lake. What makes this particularly striking is the distance between these two discovery sites, separated by thousands of kilometers, suggesting that whatever chemistry was producing these organic materials billions of years ago was not confined to one isolated puddle, but may have been widespread across the ancient Martian surface. Scientists are careful, and rightly so, to emphasize that none of this proves life ever existed on Mars. These organic molecules could have formed through purely non-biological, geological, or even meteoritic processes. The only way to know for certain would be to bring physical samples back to Earth, where they can be studied with instruments far more sensitive than anything that can currently be flown to another planet, which is precisely the ambition behind the ongoing, though technically and financially challenging, effort to eventually return cached Martian samples home. But here's the part that connects directly back to you. Standing there on the Amazonian surface 1 billion years ago, these organic molecules, whatever their origin, are extraordinarily old and extraordinarily fragile. Without a protective magnetic field or thick atmosphere, the Martian surface is bathed in cosmic radiation and solar particles that break down organic compounds over time. The molecules being discovered today survived billions of years only because they were buried deep enough within rock to be shielded from that relentless bombardment. This means that standing on the surface itself, exposed to open sky, you would be standing in one of the most radiation-soaked environments a human being has ever occupied, receiving a dose of cosmic and solar radiation many times higher than anything experienced on Earth's surface, even at the top of the tallest mountains. It's a sobering thought. The very organic clues that make Mars so tantalizing to astrobiologists today survive specifically by hiding from the world you're currently standing in. It's worth pausing here to really sit with the scale of time involved, because our brains are simply not built to intuitively grasp numbers like 1 billion years. If you compressed the entire 4.5 billion year history of Mars into a single 24-hour clock, the wet, potentially habitable Noachian period would occupy only the first few hours after midnight. And by the time you arrive on Mars 1 billion years ago, you'd already be well past 9 o'clock in the evening on that same clock, with the day of Martian history stretching on in largely unbroken silence for hours yet to come, all the way to the present moment and beyond. 1 billion years ago on Earth, for context, life existed only as simple, single-celled organisms drifting in ancient oceans. Complex multicellular life, let alone anything resembling an animal, was still hundreds of millions of years away from evolving. The dinosaurs, so often treated as the ultimate symbol of deep time, wouldn't appear for another 600 million years after that point. And yet, on Mars, 1 billion years ago was already just another unremarkable chapter in a story of slow decline that had begun over 2.5 billion years earlier still. There's something profoundly humbling in recognizing that Mars essentially finished its story of dramatic change, while our own planet's story of complex life was only just beginning. Two neighboring worlds, born from the same swirling cloud of cosmic material, took radically different paths. Earth, blessed with a larger size, a stabilizing moon, plate tectonics that continuously recycle its crust and regulate its climate over geological timescales, and a magnetic field powered by a still molten, churning core kept its atmosphere, kept its oceans, and kept the conditions necessary for life to flourish and diversify for billions of years. Mars, smaller, cooling faster, losing its magnetic shield far earlier, saw its potential for a living surface, essentially close off within its first billion years of existence, leaving behind nearly 3.5 billion years of quiet, cold persistence, the very stretch of time you'd be walking through if you truly stood there a billion years in the past. And yet, Mars was never entirely inert during this long twilight, the glaciers advancing and retreating with the planet's chaotic tilt. Volcanoes occasionally stirring, melting pockets of buried ice into brief, fleeting floods. The slow chemical dance between rock, water, and atmosphere that locked carbon away into minerals like siderite. All of this tells us that even a supposedly dead planet can remain quietly, subtly active across almost unimaginable stretches of time. It's a reminder that the line between a living world and a dead one isn't always a sharp boundary. It can be a long, slow fade, punctuated by unexpected flickers of activity, for billions of years after the main story seems to have ended. Today, robotic explorers are picking through the fossilized chemical remnants of that ancient story, piece by piece, patiently reconstructing what Mars once was and understanding, in ever finer detail, exactly what it had already become by the time you would have stood on its surface a billion years ago. Future missions, including the European Space Agency's Rosalind Franklin rover, are being specifically designed to drill deeper beneath the radiation-scoured surface than any previous mission, searching for organic material and possible biosignatures better protected from the destructive environment. Above, precisely because scientists now understand just how hostile that Amazonian surface truly is and has been for so staggeringly long. So when you imagine standing there on that cold, rust-colored plain beneath a butterscotch sky, feeling a thin, whispering wind that could never fill your lungs, surrounded by silence deeper than anything on Earth, you're not just imagining an alien landscape. You are standing at a specific quiet moment within an almost incomprehensibly long epilogue on a world that had already lived its most dramatic chapters and settled into a slow, patient waiting, still holding, buried deep within its rocks, fragments of a wetter, warmer story that ended long before you arrived and that we, on a small blue planet next door, are only now beginning to fully read.